Hi everyone! In this video we are going to discuss our other nucleophiles, so sulfur, hydrogen, and carbon nucleophiles. But additionally we're going to talk about hydrolysis reactions, which are the reverse of the previous reactions we've talked about. So for example, let's say that we have a ketal, and this will be a cyclic ketal. And remember, if we want to reverse this type of reaction, we just have to add water. And then we're also going to use a catalytic acid. And what we'll end up with is our ketone, at least in this case with the ketal. If you had an acetal, then you'd have an aldehyde. And the other product would be ethylene glycol. So let's just briefly go over the mechanism. It's going to look very similar to previous mechanisms, just in reverse. So in the first step, one of the oxygens on our ketal is going to protonate itself. So we'll end up with a positively charged oxygen. And in the next step, our other oxygen, which is unprotonated, is going to create a double bond with one of its lone pairs of electrons. That's going to cause our other carbon-oxygen bond to break, and the electrons will go up to that positively charged oxygen. So now we have a double bond to one oxygen, and that oxygen is still attached to the carbons up at the top of our ring from earlier, but now we have an alcohol at the end. Next, water is going to come in and act as a nucleophile. It's going to attack the carbonyl carbon, which will move pi electrons up to the positively charged oxygen. Okay, so we have a water molecule now on one side, and then our oxygen with the carbon chain to an alcohol on the other side. Now, similar to our previous mechanisms, one of the hydrogens on oxygen is going to move to the other oxygen. So we can just write plus minus H plus. So now we have OH on one side, and we're creating a good leaving group on the other side, which will be ethylene glycol. Okay, so now our oxygen on the left in the alcohol group is going to use one of its lone pairs of electrons to create a double bond, which will cause our leaving group to leave. So now we have our double bond again to oxygen, although we still have a hydrogen bonded to that, plus that ethylene glycol. So in the last step, we're just going to deprotonate that oxygen. So maybe water would come in and take that hydrogen. So we'll just write minus H plus here. And now we have our ketone and ethylene glycol. So again, hydrolysis is one way that you can reverse your reaction. If you were forming a ketal or an acetal, for instance, you can go back to the starting materials by using hydrolysis. So you can also do this with imines and enamines. So for instance, if you have an imine, you can just add that catalytic acid as well as some excess water. And that's going to give you back your ketone plus your primary amine. Same for enamines. If you have an enamine and you want to go back to the ketone or aldehyde, depending on, what you were using. Again, just add catalytic acid and excess water, and you'll get back your ketone and this time your secondary amine. So one practice activity that you could do is try to draw the mechanism for the hydrolysis of imines and enamines. Your textbook does have those available, but I think it's a good idea just to kind of practice going through the mechanism. And again, it will be in reverse from what we did before. Okay, so let's practice drawing out one of these mechanisms. So let's try to draw the enamine hydrolysis mechanism. So there's our enamine, and then we're going to add catalytic acid as well as excess water. Okay, but again, we're going to try to draw the mechanism down below. So feel free to pause the video and try this on your own first, and then when you're done, we'll go over it together. Okay, so what do you think the first step will be? So the first step is the alkene protonating. And we know that when a double bond is protonated, the hydrogen typically adds to the less substituted carbon. So now we have a positively charged carbon. Now there is a resonance structure that we could form here, so we could move that lone pair on nitrogen down to create a double bond. So now that positive charge will be shared between carbon and nitrogen. But additionally, remember we're using excess water. So a water molecule can come in and attack that partially positive carbon, and that will move electrons back up to nitrogen. So now we have our nitrogen on one side and our water molecule on the other. And in the next step, we're just going to move one of those hydrogens on our oxygen over to nitrogen. So we'll just say plus minus H plus. So we're trying to create a good leaving group here. All right. And then in the next step, one of the lone pairs on oxygen is going to move down to create a double bond, and we'll kick out our leaving group, which is the nitrogen group. All right, so now we've got our almost our ketone there. We still have a protonated oxygen that we've got to deprotonate. And we've also reproduced our secondary amine there. So now let's just deprotonate that oxygen, and we've got our ketone and our secondary amine. So again, this is always good practice just to work through these mechanisms. It kind of gets you used to the patterns or what to expect. So let's talk about some of our other nucleophiles. So sulfur, remember we could add a sulfur-containing nucleophile to our ketone or aldehyde. So let's say we have a ketone and we could add a thiol or two thiol groups to that ketone. So this is very similar to when we added alcohol groups to our ketone or aldehyde. But instead of alcohols or even alkoxy groups, that's also similar, we're going to end up with something called a thioketal. And then our other product is water. We could also react our ketone or aldehyde with something that looks very similar to ethylene glycol, but instead of oxygen atoms, we have sulfur atoms. So this is going to create something that looks like a ketal, except we have those sulfur atoms. So this is called a cyclic thioketal. And water is our other product. Now, remember earlier we said we could perform reduction on, or for instance, we could perform like a Wolff-Kishner reduction where we create an imine and then we reduce it so we just get an alkyl group. Well, we can do something similar with these thioketals, and we can add something called Raney nickel. And that's what's shown off to the left here. This is Raney nickel. So Raney nickel, it's a nickel aluminum alloy, and the surface of this alloy has hydrogen atoms on it. So those hydrogen atoms, so we can just kind of draw some hydrogens on here. They're just stuck in there in that material. Those hydrogen atoms are going to replace the sulfur atoms, and we're going to end up with just our alkyl group there by itself. Now, one problem with this method is that sulfur smells really bad. So if you're trying to reduce your ketone into just an alkyl group, you might want to use ethylene glycol instead. You might not want to use a sulfur-based molecule. We'll just write here, sulfur smells. So we might not want to use this method in particular, but you can if that's all that's available. But let's just make a couple notes on Raney nickel. So Raney nickel is, again, a nickel aluminum alloy, which is just kind of a mixture of the two. And the hydrogen atoms are, let's see, on the surface. Because it's a pretty porous material, so it has little pores that the hydrogen atoms can sit in. All right, so let's actually go over all of our different reduction options. So the first option is the Clemmensen reduction. The second one is our Wolff-Kishner reduction. And now we have a third option, which is our Raney nickel reduction. So the Clemmensen reduction is good for what are called aryl ketones. So that's where you would have a ketone maybe bonded to like a benzene ring something aromatic, for instance. But Clemmensen reductions don't work for anything that's sensitive to acids. So that would be any functional group that could easily react with an acid. Or let's say doesn't work. Also, the Clemmensen reduction, remember, uses mercury, which is toxic, so we want to avoid it. Additionally, Clemmensen reduction doesn't work for alkyl ketones. So that would be like, for instance, just a regular old ketone. It has to be bonded to an aromatic group there, an aryl group. So the Wolff-Kishner reduction, that is a green reaction, which is great. It works for all aldehydes and ketones. However, again, this does not work for certain functional groups that are sensitive to bases. So if something reacts really easily with a base, then this isn't going to work. And you're using hydrazine in this reaction, which is very flammable. So that's something you typically want to avoid. So hydrazine is actually what's used in rocket fuel. And then for Raney nickel, we just said that that's a porous alloy. And that works really well with all aldehydes and ketones, so that's great. It's also relatively green, so it's not too hazardous, but it is smelly. So, when you're trying to pick a reduction method, you always want to take the pros and the cons into account and see also just what's available. So now that we've gone over some of these reduction options, you can kind of see that, in chemistry, you often have to take the good with the bad, or the bad with the good, etc. So let's move on to hydrogen nucleophiles, and this is all going to be review. This is information we've learned before, which is why we're just going over it briefly. But remember, if you have an aldehyde, you can use lithium aluminum hydride or sodium borohydride with an alcohol. And that's going to, or the hydride acts as a nucleophile, which then reduces the aldehyde into a primary alcohol. Same thing for ketones. So you can use those same reagents, but this time you'll end up with a secondary alcohol. So you can also reduce carboxylic acids and esters using lithium aluminum hydride, and that will give you a primary alcohol. Now, in this chapter, we're really focused on aldehydes and ketones, but it's always good just to kind of review. Now, remember, with carboxylic acids and esters, you can't use sodium borohydride because it's not strong enough to reduce these two functional groups. So you have to use lithium aluminum hydride. So let's now talk about carbon nucleophiles. This is also review. These are reactions we've seen before. So if you have a ketone, for instance, one nucleophile that you can use is a Grignard reagent. And the Grignard reagent is going to add whatever alkyl group you have there to your ketone or aldehyde, and that's going to create an alcohol. And this will be a tertiary alcohol. Another nucleophile that we could use is cyanide. Let's see, and then we'd also need a little bit of acid there to protonate the oxygen at the end. So this is going to add a cyanide group to that central carbon. And because we have an alcohol and a cyanide group on here, this is called a cyanohydrin. Now, what's really cool is from there, you could, for instance, reduce your cyanide group by using lithium aluminum hydride, and that's going to add hydrogens to the carbon and the nitrogen. So what we end up with is a molecule with an alcohol and an amine. Another option is you can use some acid and heat. So this would be a hydrolysis reaction. And that's going to turn your cyanide group into a carboxylic acid. Let's see, I'll just draw it this way. There we go. So on that molecule, now you have an alcohol and a carboxylic acid. So there's a lot you can do with some of these reactions here. Now, in our last example, we're going to talk about something called the Wittig reaction. And this also uses a carbon nucleophile, but it's a little bit different than what we're used to. So in this reaction, you start with a ketone or an aldehyde. Either one works. And you're going to use something called an ylide. So the ylide here has a positively charged phosphorus atom that's bonded to 3 benzene rings or phenyl groups. And then it's also bonded to a negatively charged carbon, and that carbon is bonded to a hydrogen and an alkyl group. And what you get at the end that carbon group on our ylide here ends up on our double bond. So it replaces the oxygen. So you end up with an alkene, and there's a very specific way that this reaction occurs. So what you typically end up with is a Z alkene. So the two highest priority groups on either side, they'll be facing in the same direction. So let's go over how to prepare that ylide. So the first thing you start with is that phosphorus bonded to 3 phenyl groups. And you also have an alkyl halide. Now, this alkyl halide will be a methyl alkyl halide or a primary alkyl halide. So it should be a pretty simple alkyl halide. So the lone pair on phosphorus is going to be attracted to that carbon because the carbon will be partially positive due to the halogen that's bonded to it. And then the halogen acts as a leaving group. So this is an SN2 reaction because the phosphorus is attacking and then the leaving group is leaving at the same time. And that's how we get our initial kind of ylid looking group, although we're not quite done yet. So notice that in this intermediate, the carbon isn't negatively charged. And an ylid is defined as something that has a negatively charged carbon or atom bonded to a positively charged heteroatom, so something that's different. So the next step, we're going to use butyl lithium. So remember that butyl group will be negatively charged. So that can come in and grab a proton, which will leave electrons behind on carbon. And then we get our ylid. Now there is a resonance structure here where the negative charge on carbon or those lone pairs can move over to create a double bond between the phosphorus and carbon. And this would give us, let's see, a more neutral carbon and phosphorus, which is actually called phosphorine. Whereas our initial structure was called an ylid. All right, so again, when you're preparing this ylid molecule, you need that phosphorus that's bonded to 3 benzene rings or 3 phenyl groups, and then you also need a simple alkyl halide. So now that we've created our ylid, let's see how it acts as a nucleophile with a ketone or aldehyde. So we'll just draw a ketone here, and then we'll draw our ylid molecule. So that negatively charged carbon is our nucleophile. So that's going to attack the carbonyl carbon, which will move electrons up to oxygen. So now we have a negatively charged oxygen, and then on the other side we have that ylid. Oops. So here's the really cool part is the oxygen, the negatively charged oxygen, is attracted to that positively charged phosphorus. So we're going to create a little square between that oxygen and our phosphorus, which is also bonded to 3 phenyl groups. So this is called oxyphosphatane. And in the next step, the electrons between oxygen and the carbon below are going to move up, and the electrons between the phosphorus and carbon are going to move down. So we end up with phosphorus double bonded to oxygen, and then we have those 3 phenyl groups still. And then the 2 carbon atoms that are on the bottom here, those are going to now have a double bond between them. So let's just highlight what's going on here. So we're creating a double bond between oxygen and phosphorus. And then we're also creating a double bond between the carbons on the bottom of our square there. So again, we've ended up with our alkene, and it will be in the Z configuration due to that very specific kind of interchange of electrons. And then our other product is called triphenyl phosphine oxide. So a very long name. Okay, so before we stop the lecture today, let's just do a challenge problem. So in our challenge problem, we're going to start with cyclohexane, and we're going to try to make the following. Now, we're going to try to use cyclohexane and alcohols that have 4 carbons or less. All right. So the first thing that I recommend, if we go back to our reaction, our simple Wittig reaction at the top here, notice again that our carbon group on the ylide is really taking the place of the oxygen on that double bond initially on the ketone or aldehyde. So if you're working backwards, what you can do is just divide that double bond in your product and then try to figure out which side is the ylide and then which side is the ketone or aldehyde. So looking at our challenge problem here, let's divide that double bond and then try to figure out which side is the ylide and then which side is the ketone or aldehyde. Now remember, the ylide is the nucleophile, and nucleophiles should typically be simple, right? Because they're formed from alkyl halides. So they should be pretty simple. So I'll let you try to figure out, which side is which, and then try to work backwards and figure out how would you make that ylide starting with an alcohol. And then when you're done, we'll go over it together. All right, so let's work backwards. Which side do you think is the ketone or aldehyde, and which side is the ylide? So we said that ylides should be pretty simple, or the carbon group on the ylide should be pretty simple since it's acting as the nucleophile. So the right-hand side is going to be our nucleophile. So that will be our ylid, or I guess it will be part of our ylid. And the other side is going to be our ketone. All right, so let's just kind of work backwards here. Okay, so we're just going to put an oxygen on that double bond on the cyclohexane ring, so that's our ketone. And the other side, we said, would be part of our ylid. So that would mean we have carbon bonded to a hydrogen and a methyl group, right? Because we've got a methyl group and a hydrogen up there. And then because we know that we're using an ylid to go through this reaction, we know the other side here would have a phosphorus with 3 phenyl groups. Okay, but remember, we're starting with cyclohexane and an alcohol. So we need to figure out, how do we go from our ketone to cyclohexane? So we're going to do some retrosynthetic analysis again. And then how do we go from our ylid back to an alcohol? So let's start with our ketone. How would we kind of go all the way back to cyclohexane? So, I mean, there's a few different ways you could do this. Let's see. So maybe we started with an alcohol. And then just oxidized it to get our ketone. So what oxidizing agent could we use there? So since it's a ketone, we could use really any oxidizing agent, whether it's gentle or strong. So I'll just write PCC here. Okay, how do we add an alcohol to cyclohexane? Well, we might need to do a substitution reaction. Oh, I forgot to draw my big retrosynthetic arrow. So what could an alcohol substitute for? Or what type of leaving group could we use for a substitution reaction? A halogen, right? So maybe we had bromine there initially. So how would we replace that bromine with an alcohol? So we could use a strong nucleophile like hydroxide. So we could use sodium hydroxide. And let's see, is there any way to get a bromine on cyclohexane? What reaction do we know? So we could use a radical reaction, Br2 and light. Okay, so that is our synthesis for getting cyclohexane into a ketone, or converting cyclohexane into a ketone. So now let's focus on our ylid. How could we make that ylid starting with an alcohol? Well, first of all, remember when we looked at our preparation of an ylid, we're starting with an alkyl halide. But in the step after that, we're using butyl lithium to remove a proton from that intermediate. So let's just show that step first. Okay, so we're using butyl lithium to remove a proton. And actually, I'm just going to write pH 3 here. It's a little easier. Okay. So now, if we go back to our preparation of an ylide, again, the first step, we're using a simple alkyl halide, and then that pH3 is adding into the alkyl halide. Okay, so we're going to go one step back and say that we started with that phosphorus and our carbon was bonded to an alkyl halide initially. Or sorry, a halogen initially. So we could use something like bromine, right? Okay, but we want to start with an alcohol. So let's see. Oh, I'm running out of room here. I'll just go this way, I guess. So let's say instead of bromine, we started with an alcohol bonded to that carbon. How would we replace that alcohol with a bromine? How do we convert an alcohol to a bromine? We could use something like PBr3. Okay, so that's the other half of our synthesis. So obviously I didn't have very much room on my slide here, but you can always write these out on a piece of paper or in a notebook if you have a little more room there. So again, this was a bit of a challenge because we just learned about ylides and that mechanism, but hopefully this kind of helped to piece together how you prepare an ylide and then how you kind of create our product here. So it's always good to practice retrosynthetic analysis. Okay, now in our last lecture for this chapter, so the next video, we're going to talk about a reaction called the Baeyer-Villiger oxidation reaction, and we'll go over some example problems. So I will see you then.